Every star you can see tonight sits behind a distance that swallows whole human timescales without effort. The way a drop of water disappears into a lake, we treat that as an engineering problem. Faster engines, better fuel, more patience, applied for long enough. The way every hard problem in spaceflight has eventually yielded before. Humanity has already launched a machine built on that same faith. It will likely outlast the country that built it, the language stamped on its recorder, and every person who watched it leave the launch pad. That machine has now been flying for 49 years. Longer than most careers. Longer than most marriages. And by any careful accounting, it has not yet cleared its own sun's gravitational neighborhood. So, reaching another star may not be a problem that finishes inside the lifetime of anything that starts it. Not the mission. Not the institution funding it. Not the species watching from home, waiting for a signal that may arrive after everyone who sent it is gone. Here is the one number worth holding on to before anything else. Voyager 1, humanity's most distant machine, 49 years into its flight, moving at 17 kilometers every second, and still not 1,000th of the way to the nearest star beyond our own. 7 serious attempts exist to close that gap. Every one of them has already failed, each for a different, specific reason. And the reason still standing at the end is not the one most people would guess. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Right now, a little more than 170 times the distance between the Earth and the Sun, a spacecraft the size of a small car is still climbing. It launched in September of 1977, and it has not stopped since. Voyager 1 crossed the orbit of Neptune within 12 years. It crossed the heliopause, the rough, invisible boundary where the sun's own wind of charged particles finally loses its argument with the emptier material between stars. In August of 2012, every year since, ground controllers at the Jet Propulsion Laboratory have confirmed the same quiet fact by radio, across a gap now wide enough that the signal takes the better part of a day to arrive. The spacecraft is still there, still transmitting, still moving outward, at roughly 17 kilometers a second relative to the sun it left. That is fast enough to cross the continental United States in about 4 minutes. It is not fast in any way that matters for what comes next. Call it the slow arrow, a name worth keeping, because it will return, transformed, before this hour is finished. 17 kilometers a second sounds, and mostly is, an impressive number for a machine built with 1970s electronics and a plutonium battery that has been quietly decaying for half a century. It is also, measured against the distance to even the nearest star beyond our own, closer to a crawl than a flight. Voyager 1 is not aimed at Proxima Centauri. No real mission ever needs to be, and this one certainly is not. But the comparison is the fastest way to feel the actual shape of the problem this hour is built around. So it is worth making once, carefully, and then setting the exact heading aside. The spacecraft has spent 49 years earning its current distance from home. It has decades left of power for its instruments, if nothing fails first, and generous estimates give it functioning transmission into the early 2030 seconds, before the last instrument finally goes dark, whatever it becomes after that. A silent hull, still climbing, still obedient to the same simple physics that has carried it since launch. It will still be closer to the sun than to any other star for longer than anyone currently alive will be around to notice the difference. Hold that thought, not as a discouragement, but as a baseline. Everything this hour investigates is measured against exactly this arrow and exactly this speed. Because it is the fastest object humanity has ever deliberately sent toward the space between stars, and reaching a real star will require doing something to that number that nothing built so far has managed. A particular kind of vertigo waits in picturing the actual room where that number is monitored. A control room at the Jet Propulsion Laboratory in Pasadena, staffed now by engineers who study Voyager's own archived data files to relearn commands nobody currently on staff has ever had to send. The spacecraft's onboard memory is smaller than a single modern photograph. Its radio transmitter broadcasts with less power than a household refrigerator's light bulb, and by the time that whisper reaches an antenna dish on Earth, it has faded to a fraction of a billionth of a watt, recoverable at all only because the receiving dishes are enormous. The noise floor is understood with exquisite precision, and nobody in 50 years has stopped listening. That is what still transmitting actually costs, in practice, at this distance. Not a strong signal, gamely travelling, but the faintest whisper modern engineering can still recover, deliberately kept alive by a chain of specific human decisions repeated every single day since 1977. The slow arrow is not simply drifting outward on autopilot. It is being tended. Here is what 17 kilometers a second actually buys. Translated into the currency that matters. Time. Proxima Centauri, the nearest star to our own, sits about 4.24 light-years away, a little under 40 trillion kilometers. If the number is written out in full, rather than folded into a unit built specifically to hide its size, at Voyager one's current cruising speed, covering that distance would take in the neighborhood of 75,000 years. 75,000 years does not mean much as a number on its own. Almost no number that large does. It means something once it is translated into a chain of ordinary human lives laid end to end. Assume a generous 30 years between a person's birth and their own child's birth. A single link in that chain, 75,000 years, is roughly 2,500 of those links, one after another, each parent handing the same unfinished errand to the next, none of them ever seeing it arrive. Every civilization that has ever existed on Earth, from the first permanent settlements to the one currently reading or listening to this sentence, fits inside a much shorter span than that. Writing itself is around 5,000 years old. 2,500 generations is not a long weekend for a spacecraft. It is longer than the entire recorded memory of our species, repeated roughly 15 times over, before the errand is done. That is the actual size of the gap a serious interstellar mission has to close. Not very far. Which is true of almost everything in the sky, but specifically this far, measured against the fastest thing our species has ever managed to send in that general direction. Nothing about the number is a trick or a rounding exaggeration. It is what falls out of dividing one honest distance by one honest, already achieved speed. It helps to hold one further comparison in mind. Because 75,000 years is also, roughly, how long anatomically modern humans have been telling each other stories at all. Long enough that the earliest deliberate burial sites, the earliest symbolic art scratched into ochre, and the earliest evidence of language itself all falls somewhere inside that same span. A voyage at Voyager's pace would ask a project to outlast not just every government, but very nearly the entire span of behaviorally modern human culture, repeated once more from the beginning. Any serious answer to this hour's question has to reckon with a number that large before it reckons with anything else. None of this means the true travel time to a real interstellar destination has to equal 75,000 years. It means that number is the honest starting point, set by the one speed our species has actually achieved and sustained across an interstellar scale distance, rather than a speed still confined to a proposal or a simulation. Every fix examined in the rest of this hour exists specifically to attack that number, from a different angle, using a different piece of physics or engineering, and the size of the gap between 75,000 years and a single working lifetime is exactly what makes this investigation worth taking seriously in the first place. If you want to feel the number rather than simply read it, try this. Pick any single decision you made 10 years ago and notice how distant it already feels. How much of the surrounding context, the people, the reasons, the version of yourself who made it, has already quietly changed? 75,000 years is that same felt distance, repeated 7,500 times over. No engineering problem in this investigation is more honest about its own difficulty than that comparison. And none of the 7 attempts still ahead gets to look away from it. Reaching another star, then, is not a single problem waiting for a single clever fix. It is a chain of separate problems, and history already contains 7 serious, genuinely attempted answers to it. Proposals that were designed, costed, and in several cases partly built or partly tested, not daydreams sketched on a napkin. Each of the 7 solves the specific failure in front of it. Each one, examined honestly, creates a new failure exactly where the old one used to be. That pattern solve, expose, solve again is the actual shape of this investigation. And it is worth naming plainly now, because nothing about the rest of this hour will announce its own progress the way a countdown or a checklist would. No tally will mark how many remain untested at any given moment. What follows is only ever the next specific way an intelligent, well-funded attempt turned out to be insufficient, and the very particular reason why. By the end, all 7 will have failed. That is not a spoiler. It is the honest state of the field. Today, and pretending otherwise would cost this hour its only real currency. What survives past all 7 is not a solution. It is a much stranger thing. The discovery of exactly which kind of barrier is left standing once every purely physical and biological one has, in fact, been dealt with. Nothing about that remaining barrier is obvious in advance. It was not obvious to the engineers who built the first serious rocket toward the stars in equations over a century ago, and their starting point is the natural place for this investigation to begin. Because before any real hardware existed, one piece of arithmetic already knew how the story of pure propulsion was going to end. Think of the 7, for a moment, less as a scoreboard and more as a set of increasingly specific answers to a single question, are 7 separate times by 7 separate teams of serious people, decades apart, in different countries, under different flags, none of them aware how the earlier ones had already fared. Is there a way to close this gap? Each answer was the best available at the moment it was proposed. Each one was overturned not by ridicule, but by arithmetic, treaty, or biology specific enough to be named plainly. The word serious is doing real work here, and it deserves to be made explicit. None of the 7 attempts examined in this hour is a thought experiment cooked up for a magazine article or a film. Each one was designed by trained engineers or physicists, backed by an institution willing to spend real money studying it, and, in a majority of cases, tested at some scale, sometimes with real hardware, sometimes with a real launched spacecraft, sometimes with a real, still active roadmap being refined today. That standard rules out a great deal of genuinely interesting speculation about faster-than-light travel, wormholes, and warp bubbles, all of which remain outside what current physics can specify well enough to design against. This investigation stays inside the boundary of what has actually been engineered, on purpose, by people who meant it. In 1903, a self-taught Russian schoolteacher named Konstantin Tsiolkovsky published an equation that still governs every rocket ever built, including every rocket that will ever carry a piece of hardware away from Earth. The equation says something that feels almost too simple to matter, until it is applied at the scale this hour requires. A rocket's final speed depends on 2 things only: how efficiently its engine converts fuel into exhaust, and how much of the rocket's total mass is fuel to begin with. Push the exhaust out faster, and you gain speed for the same amount of fuel. Carry more fuel, and you gain speed too. But here is the catch that decides everything downstream. The fuel needed to reach a given speed does not grow in a straight line as that speed increases. It grows the way debt grows on an unpaid loan, compounding against itself, because the fuel meant to push the rocket faster is its self-weight that has to be pushed. A rocket that wants to go twice as fast, using the same engine, needs far more than twice the fuel. It needs enough fuel to also carry all of the previous fuel, which itself needed carrying, in a spiral that keeps closing in on itself the higher the target speed climbs. Real rockets already live inside a mild version of this problem. It is why nearly every launch vehicle humanity has ever built sheds most of its own mass in stages, dropping empty tanks the instant they stop earning their weight. That is the entire shape of the trap. In plain language, with no notation required, fuel to carry fuel. Tsiolkovsky's arithmetic does not care whether the destination is low Earth orbit or another star. It only cares about the ratio between the speed desired and the exhaust velocity available. And for the first serious attempt at reaching another star, that ratio turns out to be the entire story. Tsiolkovsky himself never built a rocket. He worked as a partially deaf schoolteacher in a provincial Russian town, publishing his equation in a scientific journal in 1903. The same year, the Wright brothers first left the ground at Kitty Hawk. Neither he nor they lived to see a rocket clear the atmosphere. What he left behind was not a machine, but a piece of arithmetic patient enough to outlive every specific engine anyone would ever plug into it. The same equation still checked, without modification, by every mission designer alive today, deciding how much fuel a spacecraft needs before it is allowed to leave the ground. None of the 7 fixes examined in this investigation gets to skip this arithmetic. It does not care what year a proposal was drafted, what government funded it, or how advanced its underlying physics happens to be. Any design that works by expelling mass out one end to gain momentum at the other. Whether that mass is burning hydrogen, ionized xenon, a nuclear pulse, or a fusion pellet, answers to Tsiolkovsky's equation first, before any of its own more exotic details even enter the conversation. That is why this hour begins here, with a Russian schoolteacher's arithmetic, rather than with any single rocket at all. The most obvious answer to an interstellar distance is also the oldest. Build the biggest possible version of the rocket humanity already knows how to build, and let raw thrust do the rest. Chemical rockets are, by a wide margin, the most thoroughly proven propulsion technology our species has ever developed. A well-tuned hydrogen-oxygen engine pushes its exhaust out at somewhere around 4 to 5 kilometers a second. An excellent number for reaching orbit, for reaching the moon, for reaching every planet in the solar system with enough patience. Every crewed mission in human history, without exception, has ridden on some version of this same basic chemistry. It has earned the benefit of the doubt. Scale it up, the reasoning goes, and eventually it should get a spacecraft moving fast enough to make even a stellar distance survivable within one working lifetime. More engines, more stages, more fuel tanks stacked on more fuel tanks, the way every heavy lift rocket already does when reaching for a harder target than the one before it. Tsiolkovsky's arithmetic answers that reasoning directly, and the answer is not encouraging, reaching even 1% of the speed of light, a target still tens of thousands of years short of a comfortable interstellar crossing. With an exhaust velocity of 4 or 5 kilometers a second, requires a fuel-to-payload mass ratio so extreme that the fuel alone, at any reasonable density, would outweigh every planet, moon, and asteroid ever measured in this solar system combined. Not a generous estimate. Not a rounding error. The exponential term in the rocket equation simply outruns anything chemistry can supply, long before the spacecraft has covered a meaningful fraction of the distance required. Scaling the rocket up does not soften that outcome. It sharpens it, because every additional kilometer per second of target speed multiplies the required fuel mass rather than adding to it. Chemical propulsion was never going to fail interstellar travel by a little. It fails by a margin so large that bigger stops being a meaningful word at all. There is no size of rocket, built from this chemistry, that closes the gap. The first fix does not run out of ambition. It runs out of arithmetic, and it does so almost immediately. What that failure forces is not a bigger version of the same idea. It forces a different question. If raw thrust cannot win this argument, can efficiency win it instead? A rocket that throws its exhaust out so much faster that far less of it is needed? The instinct to disbelieve this failure runs deep, which is exactly why it deserves a pause. Chemical rockets are the only propulsion technology that has ever carried a human being past the atmosphere. And every one of them, without exception, has worked exactly as designed. That track record is real. And it is also precisely why the first fix is so tempting and so wrong at the same time. Proven technology earns trust at the scale it was proven on, and the jump from planetary distances to interstellar ones is not a bigger version of the same trip. It is a change in kind, and the rocket equation is the one piece of arithmetic that treats that change honestly, without regard for how well the same engine has performed everywhere else. Efficiency, not brute force, is exactly what a different family of engines was built to deliver, and unlike the previous fix, this one is not hypothetical. Ion propulsion works by stripping electrons from a light gas, usually xenon, and using an electric field to accelerate the resulting charged particles out of the engine at extraordinary speed, commonly 30 to 50 kilometers a second, roughly 10 times what chemical combustion manages. NASA's Dawn spacecraft, launched in 2007, used exactly this technology to visit two separate bodies in the asteroid belt. Vesta and Ceres, a feat no chemical-only mission of comparable cost could have matched. Nuclear thermal designs, tested extensively on the ground by NASA and the Atomic Energy Commission during the NERVA program of the 1960s and never flown in space, offer a different trade: lower exhaust velocity than ion engines, but vastly more thrust. Useful for a heavy vehicle that needs to move quickly rather than patiently. Run the same rocket equation arithmetic with ion engine numbers instead of chemical ones, and the fuel requirement collapses by many orders of magnitude. This is a genuine, measured improvement, not a rounding trick. It is the entire reason ion propulsion exists and continues to fly on real missions today. The catch is thrust, not efficiency. An ion engine pushes with a force often compared, fairly, to the weight of a sheet of paper resting in your palm. Dawn needed years of continuous, patient thrusting to build up modest speed changes that a chemical engine could deliver in minutes. Scale that same gentle push across the distance to another star, and the mismatch becomes the whole problem. Even at ion engine exhaust velocities, and even granting decades of uninterrupted thrust that no spacecraft has ever sustained, the resulting cruise speed still leaves the crossing measured in many thousands of years, not hundreds. Nuclear thermal engines do not rescue the timeline either. Their exhaust velocity, in the range of 8 or 9 kilometers a second, is higher than chemical propulsion, but still far short of what closing an interstellar distance within any recognizable human institution's lifetime would require. Both engines are real, both have been tested, and both, honestly assessed against the actual distance involved, still leave the voyage measured in an interval no funding body has ever operated across. The problem, once again, is not imagination. It is the stubborn relationship between exhaust velocity and travel time. Refusing to bend far enough, no matter which tested, real-world engine supplies the number. If steady, continuous thrust cannot win this argument either. The next serious idea available is not a steadier push. It is a much more violent one. Dawn's own mission record makes the trade vivid without needing a single extra number invented for effect. Its ion engine, thrusting almost continuously for years at a time, ultimately delivered a change in velocity larger than any chemical mission before it, on a fraction of the propellant, Genuinely the most fuel-efficient spacecraft NASA had flown to that point. And still, the same engine, run at full patience for the whole of its operational life, could not have shaved more than a rounding error off of 75,000 years. Efficiency solved the fuel problem beautifully. It left the clock almost untouched. Every engine considered so far has tried to solve the rocket equation by refining a continuous flame. The next serious idea abandons that entirely and asks a stranger question. What if propulsion did not need to be continuous at all? A controlled series of small explosions, each one detonated behind the spacecraft and absorbed by a heavy pusher plate, could in principle deliver far more thrust than any steady burning engine, trading a smooth push for a rapid drumbeat of individual, survivable shocks. The idea sounds closer to demolition than to spaceflight, and for exactly that reason, it is worth taking seriously. Nuclear pulse propulsion was the one approach in this entire investigation that stopped being a proposal and became real, funded, government hardware, tested with actual detonations rather than simulations alone. The physics behind it is almost embarrassingly direct compared to everything examined so far. Instead of burning propellant gradually across minutes or years, release the enormous energy of a nuclear reaction in a single, brief pulse, and let a shock absorber the size of a small building catch the blow and translate it into forward motion. Repeat that pulse every few seconds during the accelerating phase, and the cumulative thrust dwarfs anything chemical or ion propulsion could offer in the same span of time. That idea did not stay on paper. It became one of the strangest real engineering programs of the Cold War, and it is the next serious attempt this hour has to examine on its own terms. Not dismissed in advance, not treated as a curiosity, but given the same fair hearing already extended to chemical rockets and ion engines. The shift in thinking required to take this seriously is worth naming on its own. Every engine examined so far tried to make an explosion behave like a flame, contained, gradual, metered out in a smooth, continuous stream. Nuclear pulse propulsion abandons that instinct entirely and asks the opposite question. What if the ship simply learned to survive an actual explosion, over and over, faster than intuition says any structure reasonably could? That is not a minor variation on the earlier candidates. It is a genuinely different philosophy of how to push something through space, and it deserves to be judged on its own terms rather than folded into the same category as a bigger chemical rocket. A useful way to hold the difference. Chemical and ion engines both try to be gentle, trading violence for control. Nuclear pulse propulsion gives up on gentleness entirely, and instead tries to be survivable, betting that a well-engineered shock absorber can turn even a genuinely violent event into something a crew could ride through repeatedly. That bet is either brilliant or reckless, depending entirely on whether the engineering behind it holds, which is exactly the question the next chapter takes seriously. A specific, almost unbelievable image sits at the center of this idea, worth holding in mind before the history behind it. A spacecraft the size of an office building riding upward on a rapid, rhythmic string of nuclear detonations, each one absorbed by a plate thick enough and shock-mounted well enough that the crew inside would feel the ride as a firm, repeated jolt rather than an explosion at all. Nothing about that image belongs in a symbolic or metaphorical register. Physically tested by people entirely serious about building it for real. Project Orion began in 1958 at General Atomics, under the direction of physicist Ted Taylor, with theoretical work contributed by Freeman Dyson, who took a year away from the Institute for Advanced Study in Princeton to help design it. The design that emerged called for a spacecraft weighing thousands of tons, propelled by ejecting small nuclear charges, on the order of 1/10 of a kiloton at launch, scaling up to 20 kilotons once the vehicle had built speed. Behind a pusher plate roughly as thick as a ship's hull, detonations near the ground would come almost once a second. As the vehicle climbed and its own inertia grew, the pace would slow, while each individual charge grew larger. On paper, the numbers were extraordinary. Enough delta V, in principle, to reach a meaningful fraction of the speed of light, using technology that, unlike fusion or antimatter, already existed in 1958. This was not a thought experiment confined to a chalkboard. Engineers built and flew scale models using conventional chemical explosives instead of nuclear charges, proving that a pusher plate could absorb a rapid series of detonations and convert them into stable, controlled thrust without tearing the vehicle apart. Small hardware, real footage, a genuine test campaign. Project Orion earned every bit of the seriousness this hour has extended to it. What killed it was not a failure of the concept. It was a decision made in a different building entirely. In 1963, the United States, the Soviet Union, and the United Kingdom signed the Partial Test Ban Treaty, prohibiting nuclear detonations in the atmosphere, in space, and underwater. Project Orion's entire propulsion scheme depended on doing exactly that, repeatedly, in exactly those environments. American negotiators reportedly sought a narrow exception for peaceful nuclear propulsion in space. Soviet concern over how easily such an exception could mask weapons testing kept it out of the final treaty. Funding for Orion was cancelled in 1965, and no government since has revisited a design that requires open-air nuclear detonation to function. Freeman Dyson himself would later describe it as one of the only times in modern history that a major expansion of human technology was suppressed for reasons that had nothing to do with whether it would have worked. That is worth sitting with for a moment, because it is the first sign, this early in the investigation, that not every wall standing between us and another star is going to be a wall made of physics. Some of the walls are made of what people, quite reasonably, decided not to allow. And a wall built from a decision behaves very differently from a wall built from an equation. Equations do not change their minds. Decisions, in principle, can. That distinction will matter again, much later in this hour. For now, the practical consequence is simpler. The one propulsion concept that could have delivered relativistic speeds using 1960s technology was closed off by international law before it ever left the ground, and the next serious attempt would need an energy source that did not require detonating bombs in open space at all. Something else is worth flagging about what did not kill Project Orion. It was not an engineering failure. The pusher plate concept worked in every test conducted. It was not a lack of ambition. Internal proposals seriously discussed missions to Mars within the decade, and, eventually, to nearby stars within a working lifetime. A design that could have outperformed every rocket flown since was set aside not because it failed a test, but because the world, quite reasonably, decided the price of testing it further was too high. That is a different shape of failure than anything examined earlier in this hour, and it will not be the last time this investigation runs into it. Between 1973 and 1978, a team of volunteer engineers and scientists at the British Interplanetary Society, led by Alan Bond, produced the most detailed interstellar spacecraft design ever completed. Project Daedalus. Daedalus was never intended to carry a crew. It was conceived as an unmanned probe aimed at Barnard's star, roughly 5.96 light-years away, powered not by nuclear fission but by fusion, the same reaction that powers the Sun itself. Here harnessed in brief, repeated pulses rather than a continuous burn. Pellets of frozen deuterium and helium-3 would be compressed and ignited by electron beams. Dozens of times per second, each micro-explosion contained just long enough to direct its energy out through a magnetic nozzle. The design called for 2 stages and a combined vehicle mass of roughly 54,000 tons, most of it fuel, aiming for a cruise velocity near 12% of the speed of light. Enough, in principle, to reach Barnard's star in about 50 years. 50 years is, by the standards of everything examined so far this hour, an almost shockingly good number. It fits inside a single working career, start to finish, the way a mission to Barnard's star had never once fit inside anything examined earlier in this investigation. It is the first serious design in this investigation whose travel time a funding institution could plausibly commit to at the outset without needing 7 or 8 generations to see it through to the end. The number that stops Daedalus is not the speed. It is the fuel. The design required roughly 30,000 tons of helium-3, an isotope vanishingly rare on Earth but present in Jupiter's atmosphere in far greater concentration. The Society's own engineers proposed harvesting it using robotic aerostats, balloon-like mining platforms using fusion reactors of their own to heat the surrounding hydrogen for lift, floating in Jupiter's clouds for roughly 2 decades before the ship's fuel supply would even be complete. No civilization, in the full span of recorded human industry, has ever operated a continuous, unattended mining and manufacturing project inside another planet's atmosphere, let alone one intended to run for 20 years before its first meaningful output is even delivered back to the ship waiting on it. The engineering of the ship itself, difficult as it is, was never the harder half of Project Daedalus. The harder half was building, from nothing, an entire off-world mining economy just to fuel a single one-way voyage, a scale of industrial commitment no space agency, no coalition of nations has ever attempted for any purpose at all. The engineers who designed the Daedalus knew this better than anyone criticizing the project decades later. Their own final report, published in 1978, treated the Jupiter mining operation not as a footnote, but as the central open question of the entire design. The one subsystem the team could specify in principle, but had no realistic path to costing in practice, because nothing of that scale had ever been attempted anywhere, on any world, for any reason. A study thorough enough to plan a fusion rocket's magnetic nozzle in detail still had to leave its own fuel supply as an acknowledged act of faith. 4 serious attempts have now failed, and a pattern is becoming visible underneath all 4. Chemical rockets failed on raw fuel mass. Ion and nuclear thermal engines failed on thrust and cruising speed. Nuclear pulse propulsion failed on a treaty. Fusion pulse propulsion fails on an industrial project bigger than the spacecraft itself. Every one of them, in its own way, failed because the ship had to carry, or first had to manufacture, the very thing weighing it down. Step back from the specifics for a moment, because the 4 failures examined so far share something underneath their separate details that is worth naming plainly before the investigation moves any further. Chemical propulsion needed more fuel than the solar system contains. Ion and nuclear thermal propulsion needed more centuries of patient thrust than any institution has ever sustained. Nuclear pulse propulsion needed a kind of detonation the world's governments explicitly agreed to forbid. Fusion pulse propulsion needed an industrial mining operation in the clouds of Jupiter, running unattended for 20 years, just to fill the tank. 4 completely different engineering philosophies, 4 completely different eras of technology, and every single one collapsed under some version of the same underlying weight. The ship had to bring its own propellant along for the ride. That is not a coincidence of bad luck striking 4 separate teams of engineers. It is the direct, unavoidable consequence of Tsiolkovsky's equation, examined honestly at interstellar scale rather than at the scale of a single planetary mission. Any propulsion system that works by throwing mass out the back of the vehicle inherits the same exponential penalty, no matter how exotic the mass being thrown, or how energetic the reaction producing it. Chemistry, ionized xenon, nuclear pulses, fusion pellets. The fuel changes. The trap built into carrying it does not. A specific engineering term names this family of designs. Reaction, propulsion. Anything that gains momentum by ejecting its own mass, and naming it plainly, makes the shared trap easier to see. Every one of the first 4 fixes, however different their fuel or their era, belongs to that same family. What distinguishes the 5th fix, still to come, is that it steps entirely outside that family For the first time in this investigation, trading a ship that carries its own push for a ship that only has to catch one, 4 attempts is enough to notice the trap clearly. It is not yet enough to escape it. Escaping it requires asking a genuinely different question than what should the ship burn? One that removes the tank from the equation entirely, rather than simply refining what goes inside it. Notice, too, what has not yet been ruled out. Nothing examined so far says a fast, crude interstellar rocket is forbidden by any constant of nature. Each of the first 4 fixes was ruled out by a specific, nameable shortfall in fuel, thrust, treaty, or industry. The kind of shortfall that changes, in principle, as technology and policy change. That distinction will keep resurfacing, sharper each time, for the rest of this investigation. How much genuine engineering talent has already been spent reaching this point deserves its own pause. 4 separate design teams, working in 4 separate decades, with 4 separate national research budgets behind them, converged independently on the same underlying obstacle. That kind of convergence is itself a form of evidence. Not proof that the fuel mass trap is permanently unbeatable, but proof that it is not an oversight any single team simply failed to notice. It is the actual shape of the problem, confirmed from 4 independent directions. 4 attempts have now failed for versions of the same reason. The ship had to carry, or first had to manufacture, the very propellant weighing it down. The next serious idea removes that requirement by asking a question nobody in the first 4 attempts needed to ask. What if nothing is carried at all, and the push comes from somewhere else entirely? Light itself carries momentum, even though it has no mass. A beam of light striking a surface transfers a small amount of that momentum to whatever it hits. The same way wind transfers momentum to a sail, except the wind in this case can be produced deliberately from a fixed location for as long as engineers are willing to keep it running. A spacecraft built around this idea would not burn anything at all. It would simply catch light, the way a sail catches air, and let something stationed far behind it, not on board, do all of the actual pushing. Remove the fuel tank, and the entire exponential trap embedded in Tsiolkovsky's equation disappears along with it. A sail weighing almost nothing does not need to accelerate any propellant mass of its own. It only needs the light source behind it to keep shining. That single change reframes the whole propulsion problem this hour has been circling since the very first candidate, and it is the reason the next serious attempt looks nothing like a rocket at all. Sunlight has already demonstrated this effect at a modest scale, without any deliberate laser at all. Solar sails, flown successfully by Japan's Ikaros mission in 2010, and by the Planetary Society's Light Sail 2 inches 2019, gained real, measured velocity from nothing more than ordinary sunlight bouncing off a thin, reflective membrane. Neither one came close to the speed an interstellar crossing requires, because the sun's own light spreads out and weakens with distance far too quickly to push anything to a meaningful fraction of light speed. Solving that required replacing the sun with something engineered specifically, not to spread out at all. Ordinary light radiates outward in every direction from its source, weakening with the square of distance the way any spreading signal does. A laser instead holds its beam tightly coherent, so nearly all of its energy still lands on target even after covering a distance where sunlight would have thinned to almost nothing. That single property coherence, not raw power, is the entire reason a ground-based laser array can do a job the sun itself cannot. And it is the reason the 5th fix looks nothing like the light sails already tested in Earth orbit. Precision matters here. About what actually changed between the first 4 fixes and this one, because the shift is easy to state and easy to underrate. Every earlier candidate asked the spacecraft itself to carry more capability, a bigger tank, a more efficient nozzle, a more energetic reaction. The 5th fix instead asks the infrastructure left behind on Earth to carry that capability permanently on the ground, while the spacecraft itself gets simpler and lighter than anything examined so far. That inversion infrastructure instead of cargo is the single idea underneath everything that follows in this chapter. In 2016, an initiative called Breakthrough Starshot, funded by investor Yuri Milner and backed at its founding by physicist Stephen Hawking, proposed exactly this. Not one ship, but a fleet of them, each no larger than a postage stamp and weighing barely a gram. The engineering plan, developed in detail by physicist Philip Lubin of the University of California, Santa Barbara, breaks into 3 separate, individually simple pieces. First, a ground-based laser array roughly a kilometer across, generating on the order of 100 gigawatts, comparable, briefly, to the output of a large fraction of a country's entire power grid. Second, a gram-scale probe called a Starchip, carrying a camera, a radio transmitter, and almost nothing else, attached to a thin reflective sail a few meters wide. Third, a burst of concentrated laser light, lasting only minutes, pushing that sail hard enough to reach roughly 20% of the speed of light before the beam loses focus, and the probe simply coasts the rest of the way. Put those 3 pieces together, and the number that emerges is the most startling in this entire investigation so far. At 20% of light speed, a fleet of these tiny probes could reach the Alpha Centauri system, including Proxima Centauri, its nearest member, in roughly 20 years, not 75,000 years, not 50, 20. For the first time in this hour, an interstellar crossing fits inside a single human career without needing 7 or 8 generations, or even 2, to see it through. The catch is not the laser, and it is not the sail. It is the space in between. Interstellar space is not the perfect vacuum it is often imagined to be. It carries a thin scatter of dust and gas, the leftover material never gathered into a star or a planet. At ordinary spacecraft speeds, that material is a non-issue, brushed aside without consequence. At 20% of the speed of light, it stops being background and starts being a hazard that scales with velocity itself. Lubin's own published analysis puts a number on it directly. A single dust grain, roughly 1/10 of a micron across, far smaller than a human hair. Striking a starchip at that speed would punch through and melt a hole nearly 0.5 millimeter deep in a probe whose entire structure is only a fraction of that thick. For a fleet of postage stamp probes, that risk is survivable, in the way any expendable, mass-produced object can survive a percentage of losses. Send enough of them, and some fraction will make it through intact. That same math refuses to translate to anything carrying a human being. A crewed vessel large enough to sustain a person cannot simply accept a percentage loss. Every impact happens to the one hull that has to arrive whole, and the number and size of impacts only grow with a larger frontal area exposed for a far longer transit than 20 minutes of laser acceleration. Breakthrough Starshot did not fail on physics, exactly. It succeeded completely for something the size and expendability of a postage stamp, and failed completely for anything meant to carry a person home. Engineers working on the project have proposed real countermeasures, a sacrificial leading edge of beryllium copper to absorb the worst impacts, a sail folded into a narrower profile during cruise to reduce the area exposed to oncoming dust. Both help a gram-scale probe's odds. Neither one changes the underlying arithmetic for a vessel with a cross-section and a crew thousands of times larger than a starship's own. Step back again, because the 5th fix reveals something the first 4 never could, hidden as they were inside a much slower, gentler regime of speed. Every propulsion scheme examined earlier in this hour treated the space between stars as empty, a reasonable simplification at the speeds those designs actually reached, none of them faster than a small percentage of Starshot's target. That simplification stops being safe the moment velocity climbs into the range needed to make an interstellar crossing survivable within a human institution's attention span. Kinetic energy scales with the square of speed, not with speed itself. which means the same speck of interstellar dust that a slow ship would barely register becomes, at relativistic speeds, indistinguishable from a targeted impact. This is the genuinely new kind of failure this investigation has reached. The first 4 candidates failed because they could not gather enough speed. The 5th candidate gathered exactly the speed required, cleanly, using real hardware with a real published engineering roadmap, and discovered that the interstellar medium itself becomes a hazard precisely in proportion to how well the propulsion problem gets solved. Faster is not simply better from here on. Faster is also, unavoidably, more dangerous, in a way no amount of additional engine cleverness removes. The dust hazard is not unique to laser sails either, once it is named clearly. Any design in this investigation capable of reaching a meaningful fraction of light speed, a hypothetical, far larger nuclear pulse or fusion pulse ship pushed hard enough, for instance, would eventually run into the same physics, at the same threshold, regardless of what accelerated it there. Breakthrough Starshot simply reached that threshold first, because it is the only one of the 7 fixes actually capable of getting a payload to relativistic speed with technology that exists today. That reversal is worth naming plainly, because it changes the shape of every remaining option in this investigation. Up to this point, every failure has come from not having enough of something. Not enough fuel, not enough thrust, not enough industrial capacity. The 5th fix is the first to fail from having too much of something instead. Velocity, past a certain threshold, stops being purely an asset and starts generating its own kind of bill. And no design examined so far has found a way to enjoy the first without eventually owing the second. There is an old, almost folk wisdom shape to that discovery, oddly enough. Every serious engineering problem tends to have some version of a sweet spot, a region where a resource is scarce enough to be precious and abundant enough to be safe. The first 4 fixes in this investigation lived entirely on the scarce side of that spot, starving for speed. The 5th fix is the first to overshoot it entirely, and the overshoot itself, not any shortage, is what closes the door. That makes the 5th fix something more useful than a single failed design. It is the moment this investigation discovered a genuine speed limit hiding inside the problem itself, not the speed of light, which nothing here has come anywhere close to challenging, but a much lower, much more practical ceiling set by ordinary interstellar dust, above which a crewed vessel simply cannot survive its own journey. Every option considered from here forward has to respect that ceiling, whether it approaches from the direction of speed or, as the next fix does, from the direction of patience instead. If speed itself keeps producing new failures every time it climbs high enough to be useful, one option remains that nothing examined so far has tried: refuse to chase speed at all and solve the distance with patience instead. This option was always available, technically, even before the first 4 attempts began. Nothing about it depends on any new engine or material invented since Voyager's own launch in 1977. What has kept it off the table until now is not feasibility. It is appeal every earlier fix promised, at least in theory, that a smart enough design could deliver a voyage within a lifetime, while this one concedes that premise from the start and asks a different question entirely. A slower ship, cruising at a modest fraction of Voyager's own velocity or a bit beyond it, avoids the dust erosion problem simply by moving too slowly for it to matter. It also avoids the worst of the fuel mass trap, because a gentler target speed asks far less of Tsiolkovsky's equation than anything the first 4 candidates attempted. What it does not avoid is time. A voyage measured in centuries rather than decades cannot be crewed by the people who launch it. It has to be crewed by their descendants, and their descendants' descendants, born, raised, and eventually buried aboard a vessel that never opens its doors to a new sky. That is the generation ship. The option every earlier failure has been quietly herding this investigation toward, not because it is elegant, but because it is what remains once raw speed has been tried in every serious form available and found wanting. It trades one hard problem, propulsion, for 3 different hard problems that none of the first 5 candidates ever had to face at all. Keeping a crew alive under radiation for centuries, keeping an entire ecosystem stable without resupply, and keeping a human population genetically and socially viable across dozens of unbroken generations. None of those 3 problems is a propulsion question at all, which is precisely why this investigation has not needed to raise them until now. Every earlier fix lived or died on fuel, thrust, treaties, or velocity. The generation ship is the first candidate whose survival depends almost entirely on biology and social endurance instead. A completely different discipline being asked to solve a problem that engineering, on its own, has already tried and failed to close 5 separate times. Honesty is owed here about the actual size of the trade being made. Slowing down does genuinely solve the propulsion half of this investigation cleanly and completely. A modest cruise speed asks so little of Tsiolkovsky's equation that fuel mass stops being the binding constraint at all. What the slow route buys with one hand, it spends with the other. Propulsion becomes easy exactly to the degree that survival becomes hard, and the rest of this investigation now has to take survival every bit as seriously as it took thrust and exhaust velocity a few candidates ago. The first of those 3 problems is not speculative. It has already been measured on a real spacecraft over a real multi-month cruise. In 2011, NASA's Mars Science Laboratory carried an instrument called the Radiation Assessment Detector on its 253-day, 560 million kilometer journey to Mars. Led by physicist Kari Zeitlin, the team publishing in Science in 2013 reported an average dose rate from galactic cosmic rays alone of 1.8 millisieverts per day during the cruise phase, roughly equivalent in accumulated radiation exposure to a whole-body CT scan every 5 or 6 days for the entire length of the trip. Galactic cosmic rays are not solar radiation, and shielding against them is a genuinely different problem than shielding against a sunburn. They arrive as individual particles moving close to the speed of light, energetic enough that ordinary mass slows them only gradually. And thick enough shielding introduces a complication of its own. A wall of the wrong material can shatter an incoming particle into a spray of secondary particles, sometimes more dangerous, collectively, than the original. Adequate shielding is possible for a mission measured in months. Curiosity's own cruise dose, extrapolated across a voyage measured in centuries rather than months, would accumulate to a lifetime exposure far beyond anything any space agency currently permits an astronaut to receive, long before a single generation aboard the ship had lived out a normal lifespan. Put concretely, NASA's own career radiation limits for astronauts, calibrated to keep lifetime cancer risk within an accepted margin, are measured in a small number of total sieverts, accumulated across an entire career of missions. Curiosity's cruise phase dose rate alone, held constant and unshielded for even a single additional decade beyond its actual 253-day trip, would already approach that same career ceiling. A sobering comparison, given that a generation ship crew member would be living inside that same radiation environment not for a decade, but for an entire lifetime, one of dozens stacked back to back across the full voyage. Solving that problem is not, in itself, impossible. Thicker shielding, better materials, hulls packed with water or hydrogen-rich polymer absorb a meaningful fraction of the dose. But every added layer of shielding is added mass, and added mass is exactly the quantity every one of the first 5 candidates has already shown this investigation how expensive to carry. Radiation does not sink a generation ship on its own. It does confirm that the ship is not simply a slower rocket. It is a permanent, occupied structure that has to solve, for centuries without interruption, a problem the rest of human spaceflight has only ever had to solve for months at a time. Zeitlin's own team was careful to frame their result as a floor, not a ceiling. Curiosity's instruments sat behind the modest shielding of an ordinary spacecraft hull on a comparatively short cruise during a period of relatively ordinary solar activity. An occasional violent solar storm, of the kind Earth's own magnetic field routinely absorbs without anyone on the ground noticing, would add a sudden, severe spike on top of that steady background dose. A risk a multi-century voyage would have to survive not once, but repeatedly, indefinitely, for as long as the ship kept flying. Before this investigation goes any further into the physics of a ship that must sustain itself for centuries, it is worth resting, briefly, on a much smaller experiment, already run, in full, right here on Earth. In September of 1991, 8 people sealed themselves inside a 3-acre structure of glass and steel near Oracle, Arizona, called Biosphere 2, a name chosen because Earth itself was Biosphere 1. The project, conceived by ecologist John Allen, was meant to demonstrate that a fully closed ecological system, sharing no air, water, or nutrients with the outside world, could sustain human life indefinitely. It was, in miniature, exactly the ecological half of the generation ship problem, tested with real people, real crops, and a real sealed door. 2 weeks into the mission, one of the 8 crew members, Jane Poynter, caught the tip of her left middle finger in a rice threshing machine and lost it. Doctors inside the facility could not reattach it, and after some hesitation, she left through the airlock for outside surgery. Breaking, however briefly and however necessarily, she returned through that same airlock as soon as her treatment was finished, back into a dome she had every practical reason to distrust, because leaving for good was never treated, by her or by the rest of the crew, as a real option. There is something genuinely striking in that decision, worth sitting with rather than rushing past. A person choosing to reseal herself inside an experimental structure that had already drawn blood, because the mission still mattered more than the risk it had just demonstrated. Consider what that choice actually required of her, in ordinary human terms rather than mission terms. She stepped back through an airlock into the same building where the injury had happened, past the same machines, to resume the same daily work, with no promise that the next accident would be any less serious or any easier to treat from the inside. Whatever this investigation eventually concludes about institutions, treaties, and centuries, it is worth remembering that the smallest, most human version of the same commitment, choosing to stay sealed inside something difficult on purpose, because the goal still felt worth it, has already been tested at least once by one person in an Arizona desert in 1991. The larger failure came slower, and it came from a source nobody on the design team had modeled. Oxygen levels inside the sealed biosphere began falling almost immediately, and kept falling from an initial 20.9% down to roughly 14.5% by January of 1993, 16 months into a planned 2-year mission, and low enough that crew members reported symptoms resembling high-altitude sickness. Outside investigators eventually traced the cause to the facility's own soil. Microbes in the rich compost used for the crops were consuming oxygen and producing carbon dioxide far faster than anticipated, and a significant share of that carbon dioxide was then being absorbed by the exposed concrete throughout the structure, pulling the gas, and the oxygen bound up with it, out of circulation entirely. Nobody had designed the concrete to behave as an unplanned second lung, quietly breathing in the wrong direction. In January 1993, engineers injected oxygen from outside to bring the level back to safety, ending, in that single act, the experiment's claim to being fully closed. 2 years, 8 people, and a fully funded, carefully engineered attempt at closed-loop life support. And the system still needed outside intervention to keep its crew breathing normally. That is not a mark against the team that built it. It is the clearest evidence available that closed ecological sustainability remains, even now, an open engineering problem on a planet already covered in a functioning one. The specific failure is worth sitting with a moment longer, because it did not come from anything dramatic. Nobody miscalculated the size of the crops or misjudged how much oxygen 8 adults would breathe in a day. The soil itself, chosen deliberately for its richness, hosted a community of microorganisms nobody had characterized in enough detail beforehand, respiring faster than any model had predicted against a building material nobody had tested for its appetite for carbon dioxide. A team of ecologists, engineers, and physicians, given years to prepare and an essentially unlimited design budget, still missed a chemical relationship between soil and concrete that took over a year of live operation to reveal itself. Biosphere 2 is sometimes retold as a story about failure and sometimes as a story about resilience. The crew did, after all, complete the full 2 years, oxygen injection and all. Both readings miss the detail this investigation actually needs. The interesting fact is not that Biosphere 2 struggled, it is that a closed ecological system, built with the specific goal of sustaining human life indefinitely, could not predict its own oxygen chemistry in advance, despite every advantage a fixed structure on Earth's surface enjoys and a generation ship never will. Gravity, access to outside expertise the moment something went wrong, and the option, however costly to the experiment's purity, to simply open a door. A generation ship traveling between stars has none of those advantages. It cannot call for outside help. It cannot inject anything from beyond its own hull, because there is nothing beyond its own hull for centuries in any direction. Whatever chemistry goes wrong inside, it has to be caught, understood, and corrected entirely by the people already sealed inside, for far longer than 2 years, across far more unpredictable interactions than one dome's worth of soil and concrete. Scale matters here, in a direction that might seem counterintuitive at first. A larger, more complex biosphere does not necessarily behave more predictably than a small one. It simply has more interacting parts capable of producing a surprise nobody modeled in advance. Every additional crop, every additional microbial community, every additional recycling loop a real generation ship would need, beyond Biosphere 2's 3 acres, is one more opportunity for a second concrete and soil relationship nobody thought to check for, and one more chemistry problem that, unlike Biosphere 2's, would have nobody standing outside the dome able to diagnose it. Closed-loop life support, in other words, is not a solved problem waiting to be scaled up. It is an unsolved problem that has only ever been tested at the smallest scale humanity has attempted, for the shortest duration a serious trial has required. And it already produced one surprise nobody had modeled. A ship expected to remain sealed for 20 generations inherits that same uncertainty, multiplied by a length of time no closed system on Earth has ever come close to attempting. A specific irony sits inside this comparison, worth dwelling on, because it cuts against the intuition that a generation ship's isolation is its main defense. Biosphere 2 sat inside the most forgiving possible environment for a closed system test. Full sunlight for the crops, Earth's own gravity holding everything in place, a breathable atmosphere waiting immediately outside the seal in case of true emergency. A real generation ship gets none of those free advantages. Its light has to be generated or captured deliberately. Its gravity, if it has any, has to be engineered through rotation or acceleration rather than inherited from a planet. Its atmosphere, if the seal ever truly fails, has nothing outside it at all. None of this argues that closed ecological life support is impossible. Later, smaller, closed system experiments, China's Lunar Palace 1 and Russia's long-running Bios 3 facility among them, have run shorter, more tightly monitored trials with steadier results, refining exactly the kind of chemistry Biosphere 2 got wrong the first time. What none of them has done yet is run for longer than a few years, with no possibility of outside correction the way an actual interstellar generation ship would have to. Air and radiation are not the only things a generation ship has to keep steady for centuries. It also has to keep its own population, a closed, finite group of people with no way to bring in anyone from outside. genetically and socially viable across dozens of unbroken generations. And here the science does not even agree with itself. In 2003, spaceflight engineer John Moore estimated a minimum crew of somewhere between 150 and 180 people, based on standard population genetics rules of thumb. In 2018, astrophysicist Frederick Marin and physicist Camille Balufi, using a purpose-built Monte Carlo simulation called Heritage, modelled a 6,300-year voyage toward Proxima Centauri b and found that a starting crew as small as 98 could, under their model's assumptions, reach a full 100% success rate, while a crew of 32 collapsed to 0% success in every single simulated run, doomed by unavoidable inbreeding. Neither number stood unchallenged for long. Marin's own 2018 model did not yet include genetic drift or mutation accumulating across the centuries. A follow-up study in 2021 added those parameters and revised the safe starting range upward to somewhere between 100 and 500, while noting that the ship's total living capacity matters just as much as its starting head count. Separately, in 2013, anthropologist Cameron Smith reviewed the existing literature, built his own model accounting for accidents, disease outbreaks, and at least one serious population-wide catastrophe over a much shorter hypothetical voyage of about 150 years, and arrived at a minimum in the tens of thousands, an estimate a full order of magnitude larger than anything the earlier genetics-only models had ever produced. 4 separate, serious, peer-reviewed studies. 4 genuinely different answers, spanning from under 100 people to well over 10,000, and every later study exists specifically because it found the previous one's assumptions incomplete. That disagreement is not a sign of sloppy science. It is a sign that nobody has actually solved this problem yet, that the honest answer to how many people does a generation ship need is still being revised in public by the researchers closest to it, each new paper correcting the last rather than confirming it. The size of that disagreement matters as much as any single number inside it. A factor of 2 between competing estimates is an argument about details. A factor of 100, which is roughly the gap between Marin and Balufi's 98 and Cameron Smith's tens of thousands, is an argument about whether the fundamental shape of the problem has even been correctly identified yet. Every earlier fix in this investigation had, at minimum, an agreed-upon number to argue about. This is the first one where the experts cannot yet agree on the right order of magnitude. One detail buried inside the disagreement deserves to be pulled out on its own. Capacity, not just head count, keeps recurring across every serious revision of this question. A ship sized only for its starting population has no room to grow past a genetic bottleneck if one occurs, and a ship sized generously enough to buffer against one becomes, immediately, a much larger and more expensive vessel to shield, feed, and keep breathing for the length of the journey. The population problem and the ecology problem, treated separately for the sake of clarity in this investigation, do not actually separate cleanly inside a real design. They compound, put the 3 pieces back together, and the generation ship stops being a single invention and becomes a single design that has to solve shielding, closed ecology, and population genetics simultaneously for as long as the voyage takes. None of the 3 problems, examined alone, looks impossible. Radiation shielding is a matter of mass and material, both improvable with better engineering. Closed ecology is a matter of chemistry and monitoring, both improvable with better sensors and a few decades of accumulated experience beyond what one dome in Arizona managed. Population viability is a matter of genetics and social planning, both, in principle, subject to careful design rather than accident. The difficulty is not any one of the 3, it is that all 3 have to hold, without failure, at the same time, for a span of centuries longer than any tested system has ever been asked to run continuously. Biosphere 2 could not keep its own air chemistry predictable for 2 years. With outside help available the moment the numbers turned bad, a generation ship needs the equivalent of that same closed system to hold for 20 or more consecutive generations entirely without outside help, while simultaneously carrying enough shielding mass to keep centuries of cosmic ray exposure survivable, while simultaneously sustaining a population whose safest minimum size the relevant researchers cannot yet agree on to within 2 orders of magnitude. Success requires all 3 systems to fail 0 times, for a duration during which every closed system Earth has ever built has, eventually, needed an outside hand. That is what kills the 6th fix. Not a single flaw, but the requirement that 3 separate, individually manageable uncertainties all resolve favorably, continuously, for longer than any one of them has ever been tested. A slower ship solved the propulsion problem cleanly. It did so by trading one difficult, well-understood kind of failure for 3 harder, poorly understood ones, and asking all 3 to behave for longer than human engineering has ever demanded of anything built to keep people alive. None of the 3 sub-problems, taken on its own and judged fairly against where the relevant research actually stands today, is being treated unfairly by this verdict. Radiation shielding improves, gradually, with every new material tested. Closed ecology improves, gradually, with every successor to Biosphere 2, that runs a little longer and a little steadier. Population modeling improves, gradually, with every new paper correcting the last. The generation ship does not fail because any one of its 3 foundations is weak today. It fails because the design demands all 3 to be essentially solved simultaneously before a single crew member is ever asked to step aboard. A bar none of the 3 fields has yet cleared on its own, let alone together. A specific kind of arithmetic deserves to be stated plainly here, because it is easy to lose inside 3 separate stories. If each of the 3 systems, shielding, ecology, population, had, generously, a 99% chance of holding steady across any given decade of the voyage, the combined chance of all 3 holding simultaneously across even a few centuries falls fast, the way any chain of independent probabilities does, multiplying down toward improbability rather than adding safely upward. Nothing about the 6th fix requires one dramatic catastrophe. It only requires the ordinary, patient math of long odds, repeated often enough against a mission with no chance to restart if any single link gives way. 6 serious attempts have now failed, and the failures have followed their own quiet escalation. The first 4 failed at the level of fuel and hardware. The 5th failed at the level of the space between the stars itself. The 6th failed at the level of biology and time. The ship itself cannot outlast the frailty of the people riding inside it. Across the centuries, the slow route requires. Notice the direction this escalation has been moving in, because it is not random. Each fix has failed at a level closer to the crew and farther from the engine room. Fuel and treaties are the ship's own business, solvable in a workshop or a negotiating room without ever asking what a passenger experiences. Dust erosion already involves the environment outside the hull. Radiation, ecology, and genetics involve the bodies inside it directly. The 6th failure is the first one this investigation has reached that cannot be solved by redesigning any single system in isolation, because the thing failing is the crew's own relationship with time itself. 2 options remain once time is named as the actual obstacle. Rather than fuel, ecology, or genetics, the first is to accept that time and hand the voyage to enough consecutive generations to absorb it. The option this investigation has just spent 3 chapters testing and watched fail. The second is stranger, and it has not yet been raised at all in this hour. Instead of asking the crew to endure the centuries a slow voyage requires, ask whether the centuries themselves can somehow be made to matter less to the people living through them. Nothing about that second option was available to any of the first 6 attempts. Chemical rockets, ion engines, nuclear pulses, fusion pulses, laser sails, and generation ships all treated time as a fixed, external quantity, a number the design either beat or did not. The 7th and final candidate this investigation examines is the only one that questions whether the number itself is as fixed as it appears, and it does so by reaching for the one branch of physics nothing so far in this hour has needed: relativity, applied not to distance or fuel, but to the clock the crew carries with them. If the ship cannot outlast its crew's biology, one lever remains that nothing examined so far has actually pulled: not building a better ship, and not building a better ecosystem, but changing the crew's own experience of how long the voyage takes. Not by making anyone age more slowly in any biological sense, by moving fast enough that time itself, according to well-established physics rather than any biological trick, passes differently for the people making the trip. Notice how far this investigation has already travelled from its own starting point. The first candidate asked whether a bigger engine could win an argument about fuel. The 7th candidate asks whether physics itself, applied cleverly enough, can simply dissolve the question of how long a voyage feels like it takes. That is a genuinely different order of ambition than anything the earlier 6 attempted, and it deserves the same careful, unhurried hearing already given to a nuclear pulse spacecraft and a fusion probe mined from the clouds of Jupiter. Special relativity, confirmed by measurement for more than a century, predicts that a clock moving at a significant fraction of the speed of light runs slow relative to a stationary observer watching from outside. The effect is not an illusion of instruments. It is a genuine difference in the passage of time itself, verified repeatedly using particle accelerators, atomic clocks flown on aircraft, and the GPS satellites in orbit above Earth right now, whose onboard clocks require a real, measured relativistic correction to keep working accurately. Apply that effect to an interstellar crew traveling close enough to the speed of light, and the 7th fix seems, briefly, to dissolve every biological objection raised against the 6th. A ship cruising at 99% of light speed experiences time running roughly 7 times slower than an observer left behind. Push that closer still, to 99.9% of light speed, and the factor climbs past 20. A crew experiencing only a handful of years on their own clock could, in principle, cover a distance that an outside observer would measure as taking far longer. No generations required. No closed ecology asked to run for centuries. No radiation dose accumulated across a lifetime nobody aboard would actually have to live through. The 7th fix does not survive contact with the very physics that makes it work. Relativistic time dilation and the cost of reaching relativistic speed are not 2 separate facts. They are the same fact, examined from 2 different directions. The energy required to accelerate any mass to the velocities where meaningful time dilation begins does not grow gently. It grows the way every quantity in this investigation has already grown once pushed too far, steeply and then explosively, because the kinetic energy of a relativistic object depends not on its speed alone, but on a factor that itself diverges as that speed approaches light's own, reaching the Lorentz factor needed to meaningfully shorten a crew's subjective voyage. For anything with the mass of an actual crewed vessel rather than a gram-scale probe requires an energy budget that exceeds every propulsion scheme already examined in this investigation. Combined, the 7th fix does not remove the barrier this investigation has been circling since the very first candidate failed. It restates it, in a more elegant form, at a higher price. Slowing a crew's experience of time and paying for the speed required to do so turn out to be the same transaction, priced in the same currency every earlier fix already found unaffordable. A strange, almost circular elegance sits inside how the 7th fix fails, worth pausing on before moving past it. Every earlier candidate in this investigation failed by running into a wall built from something outside itself. A treaty, a dust grain, a soil microbe. The seventh candidate is the first to fail by running into a wall built from its own defining feature. The very relativity that makes time dilation real is the same relativity that makes the energy required to produce it to climb without any known upper limit as speed approaches light's own. It does not fail despite being elegant. It fails because the elegance and the cost were never actually two different things. 7 serious attempts, 7 specific deaths, each one different from the one before it. Chemical propulsion collapsed under its own exponential fuel requirement. Ion and nuclear thermal engines collapsed under thrust, too gentle to matter at this scale. Nuclear pulse propulsion collapsed under an international treaty. Fusion pulse propulsion collapsed under an industrial mining project bigger than the ship itself. Laser-driven light sails collapsed under the physics of dust at 1/5 of the speed of light. The generation ship collapsed under 3 compounding uncertainties in shielding, ecology, and genetics that no closed system has ever resolved simultaneously. Relativistic time dilation collapsed under the same energy bill every earlier fix already found unpayable, wearing a more elegant disguise. That is worth sitting with as a full set, rather than as 7 separate footnotes, because a pattern only becomes visible once all 7 are laid beside each other. Every single one of those 7 failures happened at the level of engineering, logistics, biology, or a specific, nameable human decision. Not one of them happened because a law of physics stood up and forbade the destination outright. Lay the 7 side by side once more, in the order this investigation actually met them, and a second pattern emerges alongside the first. The failures grew steadily more human as the physics grew steadily more solved. A fuel shortage is the most impersonal kind of failure there is. Pure arithmetic, indifferent to who is asking. A banned test, an unbuilt mining economy, a still disputed headcount, and an energy bill nobody can pay are each, in their own way, a story about people, what they decided to forbid, what they have not yet built, what they cannot yet agree on, what they have not yet found a way to afford. The deeper this investigation dug into propulsion, the more human the remaining obstacles became. A trend line worth remembering going into the next chapter. It would be tempting, arriving here, to treat that as the end of the story. 7 attempts, 7 failures, case closed, another star simply out of reach for reasons too varied and too stubborn to ever line up in humanity's favor at the same time. That would be the wrong lesson to take from an otherwise carefully built investigation. And the reason it would be wrong is the single detail this hour has been quietly gathering evidence for since the very first candidate. What kind of barrier, exactly, each of the 7 turned out to be. A useful test for telling the 2 kinds of barrier apart is simply to ask, of each failure in turn, whether more time alone would have changed the outcome. Give the treaty negotiators of 1963 a different set of anxieties, and Project Orion might have flown. Give Jupiter's atmosphere a different composition, and Project Daedalus might have found its fuel closer to home. Give population geneticists another decade of data, and the minimum crew debate might already be settled. Every one of those counterfactuals is at least imaginable. No comparable counterfactual exists for a law of physics. There is no version of 1905 in which a differently negotiated treaty lets mass travel faster than light. That distinction is easy to miss while walking through 7 failures one at a time, because each individual failure feels, in the moment, like the universe closing a door. Laid end to end, they tell a different story. No law of conservation, no fundamental constant, no principle of relativity or thermodynamics ever said reaching another star was forbidden. Every one of the 7 attempts was stopped by something considerably more specific and considerably more human than a law of nature. A fuel requirement nobody could source, a thrust too gentle to matter at scale, a treaty signed in 1963, a mining operation nobody has ever attempted, a hazard that scales with velocity, an ecological and genetic uncertainty no closed system has resolved, an energy bill that grows faster than any propulsion scheme can pay it. Every single one of those 7 barriers is, at least in principle, a moving target, solvable by better materials, more capable industry, revised treaties, deeper genetic modeling, or propulsion concepts not yet invented. None of them are moving targets on the timescale of a single funding cycle or a single human lifetime, which is precisely why all 7 have failed so far. But hard, and not yet solved, is a fundamentally different category of barrier than forbidden by the laws of physics. And this investigation has now spent 7 serious attempts confirming that reaching another star belongs entirely to the first category, not the second. Compare that to a genuine example of the second category, just so the difference is unmistakable. No amount of engineering will ever build a machine that produces more energy than it consumes, because that would violate conservation of energy itself, not merely exceed our current materials or budgets. Nothing examined in this entire investigation resembles that kind of wall. Every one of the 7 failures, reread carefully, is a sentence that ends with a fixable noun, a treaty, a mining operation, a dust grain, a head count nobody agrees on. Never a sentence that ends with a constant of nature refusing to bend. This is also the moment to say plainly what this investigation has deliberately left out. Ideas like faster than light travel through a warped region of space-time remain. For now, outside the category of seriously engineered attempt, this hour has held every candidate to. Real physics can write the equations describing such a thing, but no design exists yet specifying what it would take to build one, at any cost, with any material. That absence is not evidence the idea is impossible. It is evidence that it belongs to a different, earlier stage of inquiry than the 7 attempts already examined tonight, each of which came with an actual bill of materials attached. If none of the 7 engineering, biological, or physical barriers is truly final, then whatever barrier remains standing after all 7 have to be one that engineering, biology, and physics cannot solve on their own. That kind of barrier exists closer to home than any star, and this investigation's own record already contains a clean example of exactly what it looks like. Construction on Cologne Cathedral began in 1248. In what is now Germany, intended from its first stone to be among the largest and most ambitious buildings ever attempted in Europe. Work continued for more than 2 centuries, financed and organized across shifting political leadership, until 1473, when construction on the South Tower simply stopped. Funding had dried up. The Reformation was reshaping religious priorities across the region. Gothic architecture itself had fallen out of fashion. For the next 369 years, the cathedral stood unfinished. Its South Tower, capped by a massive wooden construction crane, left in place atop the incomplete stonework, visible across the Cologne skyline for so long that generations of residents grew up never having known the building any other way. The crane became, by long habit, simply part of the cathedral's silhouette, an unintentional monument to an interrupted project, standing in for its own uncertain future. Measure that gap against ordinary human memory, and its true size becomes clearer. 369 years is roughly 12 consecutive human generations, each one born, raised, and buried without ever seeing the tower they walked beneath finished, or knowing for certain that it ever would be. Every one of those generations inherited an unfinished building rather than a completed one, and every one of them, in some quiet way, chose not to tear the crane down and simply give up. That distinction, inheriting an unfinished project rather than choosing one, is worth holding on to carefully, because it describes something closer to what a real multi-century voyage would actually ask of the people carrying it than any of the 7 propulsion fixes examined earlier in this hour. Nobody born in Cologne in, say, 1600 chose to build a cathedral. They were simply born beneath one already half standing. And the building itself, silent and unfinished, did more to keep the project alive across those centuries than any single decree or decision ever could. Construction resumed only in 1842, driven less by religious urgency than by a wave of 19th century romantic nationalism that made finishing the medieval cathedral a matter of German civic pride. On October 15, 1880, 632 years after the first stone was laid, the cathedral was declared complete in a ceremony attended by the German Emperor himself. Cologne Cathedral is, by any reasonable measure, the longest continuously intended building project in recorded history to actually reach completion. It is also proof, in its own timeline, that even the most successful example available still needed a gap of nearly 4 centuries in the middle, an interruption longer than the entire history of the United States, before a single unbroken institution or purpose finally saw it through. Notice, too, what carried the project across that gap. It was not a single continuous institution holding steady for 600 years. The Catholic diocese that began construction, the guilds that carved its stone, and the 19th century German state that finished it were 3 different bodies operating under 3 different orders of loyalty, separated by a reformation and a national reinvention. What actually survived the gap was not an organization. It was an unfinished building, standing where anyone walking past could still see, in stone, exactly how much work remained. A physical record patient enough that even 4 centuries of neglect could not fully erase the original intention. Set the cathedral beside the voyage this investigation has been building toward, and the comparison sharpens rather than softens. 632 years, including its gap, is a fraction of a single generation ship's travel time to even the nearest star at the slow, patient speeds the 6 fix required. And a cathedral, unlike a ship crossing interstellar space, could simply wait, motionless, for 4 centuries without losing structural integrity, without needing continuous shielding, life support, or a self-sustaining population aboard it the entire time. No scientific institution, national government, or continuously funded research program on Earth has ever sustained a single, coordinated purpose without interruption for anything approaching the centuries a slow interstellar crossing would require. The closest known example, examined honestly, still needed to stop. Universities have operated continuously for roughly a millennium in a handful of cases, but none has spent that entire span pursuing one unbroken engineering goal, rather than an evolving, shifting mission across dozens of separate generations of scholars. Nations rise, are renamed, are divided, or are absorbed into successors within spans far shorter than a single interstellar voyage. Currencies fail. Institutional memory degrades even inside organizations that never technically dissolve. Simply because the specific knowledge required to maintain a decades-old system tends to leave with the people who built it faster than any archive fully replaces them. Space programs specifically make the same point on a smaller, more recent scale. NASA itself is barely 7 decades old, and even within that short span, entire propulsion programs, including the Nerva nuclear thermal engine examined earlier this hour, were fully funded, tested, and then cancelled within a single decade as national priorities shifted with new administrations and new budgets. A voyage requiring uninterrupted commitment across dozens of decades is asking for a kind of institutional patience that not even a single national space agency in the entire history of spaceflight has yet been able to demonstrate for one uninterrupted program. A generation ship does not only need its air, its shielding, and its population to hold steady for centuries. It needs something even harder to specify precisely. A reason to keep going that survives every one of the social, political, and economic upheavals a normal multi-century timescale on Earth has always produced, transmitted faithfully from a crew that dies aboard to a crew that was born aboard and never chose the mission for themselves. Nothing in the historical record demonstrates that this kind of unbroken transmission is possible across the timescales required. Nothing in the historical record demonstrates that it is impossible either, only that it has never yet been asked of any institution for anywhere near this long. A ship, unlike a cathedral, cannot fall silent for 3.5 centuries and simply resume later. Its reactor cannot idle unattended for generations. Its crops cannot pause. Its population cannot be reassembled from scratch by a later century's enthusiasm, the way Cologne's 19th century builders simply picked up stone carving techniques their medieval predecessors had already worked out. Whatever gap a generation ship suffers, it suffers while still moving, still consuming its own irreplaceable resources. With no equivalent of a crane left patiently on a rooftop, waiting for someone, eventually, to come back. 7 serious engineering, biological, and physical attempts to reach another star have now failed, each for a different, specific, well-documented reason. And not one of those 7 reasons was a law of physics standing in the way. That is the honest answer this investigation set out to find, and it is worth stating as plainly as the title that opened this hour deserves. The clearest way to hold the answer up beside the title: no law of physics forbids the trip. Chemistry, propulsion efficiency, nuclear pulses, fusion pulses, laser sails, closed ecosystems, and relativistic time dilation were each tried, in real designs by real engineers, and each failed at the level of fuel, treaty, industry, hazard, biology, or energy cost. What forbids the trip, so far, is something this investigation has now circled twice. Once in a spacecraft attempting to outlast its own crew across a slow, patient generation ship, and once in a 632-year cathedral that still needed to stop for nearly 4 centuries in the middle. No human institution has ever stayed intact, funded, and pointed at the same single goal for as long as an interstellar voyage itself would take. Until one does, the ship, however brilliantly its propulsion, shielding, and ecology are eventually solved, has nowhere to launch from. That is not the same as saying the voyage is impossible. It is a much stranger, more specific claim than that. Every piece of hardware this species would need has, at some point in the last 70 years, already been seriously designed, costed, and in several cases partly tested. The one component nobody has ever built, tested, or even successfully modeled is the institution required to keep funding, staffing, and believing in the mission long enough to see it through. Across governments that will fall, currencies that will fail, and generations who never volunteered for an errand handed to them at birth. Say the title's own words back against that answer, because they were chosen carefully at the very start of this hour, and they deserve to be checked rather than assumed against everything gathered since. What could stop future humans from ever reaching another star? Not what could destroy the ship. Nothing examined tonight suggests destruction is the likely ending. Not what makes the trip impossible. Nothing examined tonight found a genuine impossibility. The honest word in that title is stop. And the honest answer, after 7 serious attempts, is that the stopping power belongs to neglect, interruption, and forgetting far more than to any hostile law of physics standing directly in the way. That reframing changes what kind of question the title was actually asking all along. And it is worth restating plainly before this investigation moves toward its close. A barrier made of physics would demand a breakthrough. Some new equation, some new particle, some new understanding the species does not yet possess. A barrier made of institutional continuity demands something this species already knows how to produce in small doses, just never yet at the scale or duration required. Patience, handed down faithfully, generation after generation. Past the point where any single person involved could see the ending for themselves. The distinction matters because it changes what progress toward the goal is even supposed to look like. Progress against a law of physics arrives suddenly, in the form of a discovery, a paper published, a barrier broken, a before and after separated by a single moment of insight. Progress against an institutional barrier arrives slowly, unglamorously, in the form of an organization simply not collapsing on schedule, one budget cycle at a time, for far longer than budget cycles are used to being asked to hold. Naming the real barrier is not the same as knowing how to remove it. And honesty requires saying clearly that everything in this chapter is a model, not a measurement. There is no historical case to check it against, because nothing has ever been asked to last this long. A genuinely multi-century institution would need redundancy built into its own knowledge, not just its equipment. Every critical skill preserved in more than one mind, more than one archive, more than one format, so that losing an individual, a building, or even a generation does not erase what the mission needs to continue. It would likely need to be deliberately insulated from the political cycles that topple governments and rewrite currencies on schedules measured in decades rather than centuries. Perhaps modelled less on a national space agency, which answers to an electorate with a 4 or 6 year memory, and more on the small number of human institutions that actually have crossed several centuries intact. Certain monastic orders, a handful of universities, a small number of family-run enterprises that have deliberately structured themselves around outliving any single leader who has ever run them. None of those existing examples has ever had to keep a crew breathing, a reactor running, and a genetic pool viable while doing it. They offer, at best, a partial sketch of what unbroken transmission across centuries can look like when the thing being transmitted is a set of values or a body of knowledge. Physical survival of a sealed and irreplaceable population. Whether that same kind of continuity can be engineered around a task, this physically unforgiving is the honest, open question this investigation leaves standing. Not a discouragement, but the actual research frontier that sits past every propulsion and biology problem already examined. Precision matters about what kind of claim this actually is, because it is easy to round into either false comfort or false despair. This is not a prediction that humanity will solve institutional continuity, and it is not a prediction that humanity will fail to. It is a much narrower, more honest observation. Every other piece of this problem has already produced at least one serious, costed, partly tested design, and this one piece has not yet produced even a single serious attempt, because nobody has ever needed an institution to last quite this long before. A useful, if imperfect, place to begin looking is not spaceflight at all, but the small number of human projects already explicitly designed with multi-generational time horizons in mind. Seed vaults built to preserve crop diversity for centuries. Long-term nuclear waste storage facilities designed by committees who have had to seriously debate how to warn people 10,000 years from now in a language nobody alive today can predict, to stay away. None of these projects has been tested anywhere near its full design lifetime yet. All of them represent the first tentative drafts of exactly the kind of thinking a genuinely multi-century interstellar institution would eventually need. Proof that the question is at least being asked. In scattered, early, unglamorous ways, well before any spacecraft depends on the answer. Every one of those projects shares a quiet, common design instinct worth naming. They try to remove the need for continuous human attention rather than relying on it. A seed vault buried in permafrost. A warning marker built to be legible without language. A cathedral standing unfinished as its own reminder. Each substitutes a durable physical fact for a fragile chain of remembered intention. Whatever institution eventually carries an interstellar voyage forward will very likely need to borrow from that same instinct, building the mission's own continuity into something more durable than any single generation's memory or goodwill. It would be easy, arriving here, to hear all of this as a story about defeat, 7 serious attempts, 7 serious failures, and a final barrier that sounds even harder to engineer around than any of the 7, because it lives in politics and human memory rather than in physics. That reading misses what 7 real, well-documented attempts actually leave behind. None of them was wasted effort. The rocket equation, tested honestly against chemical, ion, nuclear thermal, nuclear pulse, and fusion pulse propulsion, and every one of those designs remains available, unchanged. The moment a genuinely new energy source makes the fuel mass problem tractable, breakthrough Starshot's laser architecture works exactly as designed for anything gram-scale and expendable, and nothing rules out hardier, self-repairing materials eventually closing the dust erosion gap for larger payloads. Radiation shielding, closed ecology, and population genetics are all active, funded fields of research today, each one incrementally improving on exactly the numbers this investigation has cited. Even relativistic time dilation remains true and useful, waiting only on an energy source nobody has invented yet. Consider, too, how unusual this position actually is, measured against most genuinely hard problems in the history of engineering. Most unsolved technical challenges stay unsolved because a critical piece of underlying science is still missing entirely. A mechanism nobody yet understands, an effect nobody has yet observed. That is not the situation this investigation has found. Every underlying scientific principle needed to attempt interstellar travel has been understood for decades, in some cases for over a century. What remains outstanding is not a gap in knowledge. It is a gap in endurance. 7 attempts did not close the case. They built the shelf. Every design this hour has examined is sitting on it, tested and costed and ready, waiting specifically on the one thing none of them could manufacture on their own. An institution able to fund, staff, and believe in the mission for as long as it actually takes. None of the 7 needs to be reinvented from nothing. The day continuity finally gets solved. Project Daedalus's fusion architecture, Project Orion's pusher plate, breakthrough Starshot's laser array. Every one of those designs exists today as a finished document, ready to be pulled back off the shelf the moment its specific missing piece arrives. That is a genuinely different position to be in than the problem is unsolved. It is closer to the problem is fully specified, and several of its component answers are already sitting in a drawer, waiting. That framing is worth holding onto specifically because of how differently it reads from where this investigation began. The opening chapters of this hour treated each failure as a closed door, one after another, until the sheer number of closed doors started to feel like an argument for giving up entirely. Revisited now, at the far end of all 7, the same 7 doors look less like a dead end and more like an inventory, parts collected, tested, and shelved, waiting on the one piece of infrastructure none of them could supply for themselves. Return, for a moment, to the machine this hour opened with, still climbing, still transmitting, still obedient to the same 17 kilometers a second it has held since 1977. Voyager 1 was never a symbol of failure. Even though it will die, silent and dark, still centuries short of any other star, it is something considerably stranger and more useful than a failure. The first small, working proof that a single human project can survive the deaths of nearly everyone who built it, launched it, and first tracked its signal home. The engineers who calculated its trajectory are largely gone. The instruments it carries were designed by people who could not have known, in 1977, whether the spacecraft would still be answering 49 years later. A little fainter each year, a little slower to respond, but still there, still counted, still climbing, run now by a generation of controllers who were not yet born when it left the launch pad. That is not interstellar travel. And it is not even close to a meaningful fraction of the distance interstellar travel actually requires. but it is the one piece of hard evidence this entire investigation can point to that a project does not have to die with its founders, that a plan, correctly built and patiently tended, can outlive the specific people who started it and still be carried forward faithfully by people who inherited it rather than chose it. The slow arrow was never going to reach another star on its own. What it proves, quietly, every single year it keeps transmitting, is that the kind of continuity this investigation eventually needed was not, after all, purely hypothetical. A small, working version of it has been flying for 49 years already. 49 years is not 600, and a spacecraft with no crew to feed is not a generation ship. The comparison is not offered as proof that the harder problem is solved. It is offered as the smallest available evidence that it is not, in principle, unsolvable. That somewhere between one unmanned probe quietly outliving its own launch team and a ship that must outlive dozens of generations, the same basic instinct, tending something you did not build for people you will never meet, is already known to work at least once. Picture, for a moment, the actual handoffs involved. Somewhere in the Jet Propulsion Laboratory's own institutional memory, a retiring engineer once sat down with a younger colleague and explained, patiently, how to read a command file written in a coding convention neither of them had used in decades. That conversation, repeated in some form across nearly 5 decades and probably a dozen or more separate retirements, is the entire mechanism keeping Voyager 1 talking. It is unglamorous, undocumented in most textbooks, and it is also, quietly, the closest thing this investigation has found to a working demonstration of the exact kind of continuity a generation ship, or the civilization funding one, would eventually need to sustain. Not for 49 years, but for as long as it takes. The question this hour opened with was simple enough to fit in a title. The honest answer that has emerged is not the one most people expect walking in, and it is not the one this investigation expected either. Several failures ago, it is not distance. Distance is only expensive, not forbidden, and expensive problems have a long history of eventually finding their price paid. It is not any single law of physics, because 7 serious, real, carefully engineered attempts were laid out, and none of them was stopped by one. It is something considerably more human, and in its own way more hopeful than a wall of pure physics would have been. An unsolved problem in institutions, in memory, in the ordinary, fragile machinery by which one generation hands a task to the next without the task getting lost, distorted, or simply abandoned along the way. 7 serious attempts is, by the end of this hour, no longer just a countable promise made in the opening minutes and paid off in the closing ones. It is the actual shape of the answer. Not one wall, but 7 doors opened in careful sequence, each closing for its own specific, documented reason, until the only door left standing turned out to be the one this investigation almost walked past without noticing. Not a door in physics at all, but a door in how long people are willing and able to keep a promise they will not live to see kept. That is a strange kind of ending for a question that began with a rocket equation and a Russian schoolteacher's arithmetic in 1903. It closes instead with something closer to a question about character than about engines. Whether a species capable of building 7 separate, brilliant, carefully engineered answers to a physics problem can also build the considerably less glamorous thing none of the 7 required. An institution patient enough to outlast the people who start it, faithfully enough that the errand never gets lost along the way. Every one of the 7 candidates examined tonight was, at some level, an answer to the question, how? How to keep a crew breathing, fed, and genetically sound for centuries. The 8th, unnamed obstacle this investigation uncovered underneath all 7 is instead a question of how long. And unlike every how question this hour resolved with an equation, a material, or a treaty, how long resolves only with time itself, spent generation after generation by people willing to keep a promise nobody is forcing them to keep. Physics does not need to be relitigated to close that gap. Politics, funding, and memory do. That is a harder kind of problem to solve on a whiteboard, and a considerably more encouraging one to end on, because unlike a law of nature, it has already been solved in small, partial, imperfect ways by cathedrals, by long-lived institutions, and by one small machine that is still, tonight, quietly proving the idea works at least once. You do not need to hold any of that as a burden on your way towards sleep. Nothing about tonight's investigation asks you to solve institutional continuity, fund a fusion probe, or personally outlast a government. It only asks you to notice, once, before the night closes over this hour, the way it closes over every hour, that the barrier standing between this species and another star turned out to be smaller and stranger than the sky itself. Not a wall, but a length of patience nobody has been asked to hold for quite this long. Yet, every one of the 7 fixes examined in this hour will still be there, unchanged, the day someone finally solves the 8th problem this investigation actually uncovered. Nothing about a treaty, a genetic study, or a dust grain expires with time the way a missed opportunity sometimes does. What changes, if it ever changes, is patience, enough of it, held by enough people, across enough generations, to let one of those 7 designs finally leave the shelf it has been resting on since the year it was drawn. Somewhere out past the orbit of every planet, past the boundary where the sun's own influence finally gives way to the emptier dark between stars, a spacecraft built before most living people were born is still climbing, still faint, still answering when asked. It is not going to reach another star. Nothing built so far is, but it will keep going quietly for as long as its last instrument holds a charge, carried by nothing more exotic than the same 17 kilometers a second it left Earth with, in the hands of people who inherited the watch rather than started it. That is a small thing, and it is also, on the scale this hour has spent examining, the largest kind of proof available. A project can survive the people who built it, if enough people, one generation at a time, simply agree to keep it. There is no need to resolve. Tonight, whether that kind of patience can actually be sustained for 6 centuries, or 20 generations, or however long the real voyage eventually turns out to require, that question belongs to people who have not been born yet, working from designs already sitting quietly on a shelf, waiting on nothing more exotic than time and attention. Tonight only asks something much smaller and much easier. To notice that the answer to an old question turned out to be more patient and more human than the question itself expected. Nothing about this hour, and nothing this investigation uncovered across its 7 attempts and one quiet, lingering 8th question needs to be carried forward as a task, or a worry, or an unfinished errand of its own. The 7 fixes will still be sitting exactly where this investigation left them tomorrow, and the year after, and for as long as it takes. The cathedral is still standing in Cologne, finished now for well over a century, no longer needing anyone's attention to remain complete. The spacecraft is still climbing, quietly, on its own schedule, tended by people who will hand the watch to others long after tonight is forgotten. None of it is waiting on you. Let it climb without you for a while. The cathedral will go on standing, whether or not you notice it again before morning. Somewhere, the next shift at the control room is already taking the watch, the way every shift before them already has, patiently, without needing anyone lying in the dark tonight to keep track. The errand is old, it is well documented, it is in good hands across several continents and several institutions at once, and it was never yours to finish alone, tonight or on any single night still to come. Wherever you are lying right now, the same inheritance applies. Quietly, without needing your attention, Whatever gets built toward another star, if anything ever does, will be built the same slow way. Two phrase, two flays, handed forward, kept, rather than finished, by people who will never see its ending and chose to carry it anyway. Somewhere above the ceiling, farther than any camera has ever looked back from, the same slow arrow is still climbing, still faint, still exactly as patient as it was at the start of this hour. Proof enough, for one night, that patience of that kind is not only possible, but already, quietly, underway. The universe will still be here when you wake up. So will we. Good night.